I'm going to talk about WAVEWATCH, and that's a project that I've been working on with colleagues at MetOcean Solutions, Emilio and Henrique. They are experts in WAVEWATCH, mainly for operational purpose. Now Emilio has moved to Australia, is in CSIRO, and I've also worked on that with Martin and Carlo. And basically, what we really wanted to do is look at all the different ways that WAVEWATCH has parameterized ice-induced wave damping, and see if some of these parameterizations emerge as performing better than others. So if you're not familiar, although I'm pretty sure most of you are, but so WAVEWATCH is what we call a spectral wave model or a phase average model. And the way this model works is that they describe the transport of this function here, the wave action density, I'm going to define in a second, on the surface of the oceans on global scale. And so it satisfies here the transport equation, as you see here. CG represents the group velocity. So that's the speed at which waves travel, essentially. And then on the right-hand side here, you have S, which is the source function, right? So if it's 0, then it's just a transport which preserves the spectrum. And if it's not 0, then you have other things happening. So this wave action density, so it is a function, of course, of space and time, but also of frequency and direction. And you can think of it as a measure of wave energy. But the phase of the waves, of course, is not resolved. That's why it's a phase average model. And the source function here, it is an attempt at representing the effect of various forcings and inhomogeneities on the transport of the wave spectrum, right? And there are many different source terms which make up S here in WAVEWATCH, although you don't have to use them all the times, but here are a few of them. So of course there is a forcing from the wind. SDS represents the dissipation due to white capping. There's some nonlinear interactions, some effect of bottom of the seafloor, especially near the coast. And of course, there's one for the ice as well. And there's others. And so WAVEWATCH, or WAVEWATCH III, I should say, is, I think, arguably the most widely used spectral wave models. There are others, but I think WAVEWATCH III is the one that is used the most. And one of the reasons that I think it's been used quite a lot, especially in our circles here, is because there has been a lot of work put in on trying to parameterize the damping of waves caused by the ice. And that can be caused through various physical processes, such as turbulent dissipation in the fluid, some viscous ice rheology, also wave scattering, and other things. And so this source term here, S ice, the standard and simplest way it is parameterized is in this functional form here. And so you have basically these 4 terms. So C here represents the ice concentration. So as you can see, it linearly depends on ice concentration. So the more ice you have, the more damping you have. That's essentially what it says here. But it says it should be linear. And alpha here, so that's this key parameter, which we call the attenuation coefficients, and that describes essentially the rate at which waves attenuate. And so WAVEWATCH currently has 14 different ways of choosing alpha, the attenuation coefficients. So, you know, if you put yourself in the position of using WAVEWATCH for the first time, that can be overwhelming. Where do you start? Which one do you choose? And so that's essentially, you know, part of what we wanted to address here. So let me just give you a brief breakdown of all these different parameterization that exist here. The first one, and this basically will so these will be listed in more or less chronological order in the way they came into the model. And so the first one that was there is basically was to treat sea ice as land, approximately. There's kind of a buffer region depending on ice concentration, but basically it treats the ice as land. And that was in the first release of WAVEWATCH, where they didn't really want to deal with the ice. And then some different parameterizations were released over time. So IC1 is the first one where alpha, the attenuation coefficient, is a constant. So it's just a number you put in. Then IC2 came in, and there's several versions of it, but in the latest version, it basically parameterizes the attenuation coefficients through some eddy viscosity parameter, which depends on the flow regime, whether it's laminar or turbulent. So that's why it depends on the Reynolds number. IC3 came out as something that was supposed to represent what the ice actually looks like, and so it's basically based on a model of a viscoelastic ice layer floating at the top of the water, which depends on a range of rheological parameters such as viscosity, elastic modulus, and so on, and thickness as well. But let's say you fix all these parameters, what you end up with at the end is alpha, which is a function of frequency, and that's the first parameterization which recognizes the importance of this frequency dependence of the attenuation coefficients, which has been observed in many different analyses. And then came out these IC4, so there are 7 of them, IC4M1 to IC4M7, and these are based on empirical. So these are empirical parameterizations, and there are 2 types. Some of them are based on model outputs, and some of them are based on direct observations. And then the last set of parameterizations, the IC5s, there are 3 of them, and they are similar to IC3. So they model the ice cover as a viscoelastic effective medium, although they are simpler than IC3. And also they give an attenuation which depends on frequency. All right, so you can count if you want, but that's 14 of them. Okay, so despite having so many different choices for choosing the ice damping in WAVEWATCH, there have not been that many studies that have compared their performance. And in fact, I think there are only 2, as far as I know, at least. And so I'll just give you a brief breakdown here of them. So the first one was by Lee et al. In 2015, where they did a hindcast of the SIPEX2 experiments in the Southern Ocean, 2012, which you may be known for the Nature paper that came out of it, led by Alison Kohut. And here they compare to the performance of 4 parameterization, IC0, IC1, IC2, IC3. So they tune the parameters of the different models to obtain a better fit, and essentially they looked at how it compared. So here what you see is the significant wave height over time. There are 2 wave buoys which were tracked, and you can see that the models are able to reproduce roughly some of the features that are observed here. And I think their conclusion was IC3 was the best performing one, although arguably IC3 has more parameters, so you can tune it more easily to fit observations. And then there is this 2020 study by Liu et al., where they looked actually at 2, so they did a hindcast of 2 wave buoy deployments. So the same one as before, SIPEX2, but also the Seastate 2015 wave buoy deployment in the Arctic. And here I'm just showing results here from their paper, looking this time, so that's a scatter plot of significant wave height at the top and mean wave period at the bottom here. And these were they compared the IC5 parameterizations. Here there are only 2 of them. So the middle one here, that's IC5M1, and the last one here is IC5M3. And the one here at the front here, that's an extra one they run where they remove the ice entirely, which is a nice one to have for comparison purpose. And what they found here is that, yeah, it seems like the model is doing a fairly good job, although they didn't really resolve the small wave energy. But if you look at the mean wave period, there is a clear bias here where the model is clearly underestimating the mean wave period consistently. All right. And so what we did here is something very similar, but instead of just picking and choosing a few of the available parameterization, we picked all of them. So we ran hindcasts here for all 14 parameterizations of the SI source term here. And we did that for the 2017 Piper's waveboard deployment in the Ross Sea. And our goal was essentially to compare their performance and identify consistent biases in WaveWatch generated data. Okay, so why did we choose this Piper's deployment? And that's because there is a lot of data that came out of it. It was so it was in the ice growth season, April to July 2017, and 14 buoys were deployed. And there was a range of wave conditions and also of ice conditions observed. So there were calm, but also large storm events. There was, of course, pancake ice conditions, but also the buoys were deployed really far into the ice cover where the ice was nearly continuous in some cases. Something to say here is that wave direction was not recorded by these wave buoys, so we only look at the one-dimensional spectrum, so with respect to frequency. Okay, so we ran 15, not 14 actually, hindcasts. So the 14 hindcast for the 14 different SI parameterizations, but also we did a no ice run. So we just remove the ice and set the concentration to 0 everywhere. And again, that's a nice baseline to have here to compare our results. And so the way the hindcasts were set up here is we ran we ran a hindcast on a regional, so a nested regional run at fairly high resolutions, which was forced on its boundary by a lower resolution global run. And the concentration and thickness were actually included here and were taken from the ERA5 reanalysis. And the only thing that we looked at here were the spectra, so the wave spectra, again, one-dimensional spectra as a function of frequency only, along the buoy track. So what we wanted to do really is compare the spectra on either side for WaveWatch and the buoys. Okay, so this is just to give you an idea here of the deployment. So we had 4 wave buoys here on the west side, and then there were 9 more buoys here on the eastern side, which were released at 2 different time periods here, and you kind of see their tracks over time. This is just a snapshot here. I think this one was taken on 15th of June, but of course some of the buoys had died already by then, and some just kept going afterwards. Okay, so let's get into it. So what we obtained from this analysis was 3,898 wave spectra, which were collocated as with the ones recorded by the buoys. And we had that for all 15 hindcasts. So that's a lot of data to go through. But the first thing I thought I would do here is actually, well, what if we just average all these spectra together and see if something just interesting comes out? And that's what we have here. So here, this is just the average spectrum. So for each wave frequency, just the average over these 3,898 values. And already something interesting is happening here. So the data from the boys is these crosses, and then you have all these different models which are all over each other here. But what we can see here already is that there's clear biases both at low frequency and high frequency. It seems at low frequency, so the model seems to significantly underestimate these spectral values here, but at high frequency, it's the other way around. The model seems to overestimate spectral amplitudes. So at low frequency, we potentially explain that by an issue with the wave buoys, and that's based on some earlier analysis we've done of the wave buoys, which shows mixed results at very low frequency, in particular below 20-second wave periods. So what we did is we just cut off the spectra here at this 20 seconds, so 0.05 hertz frequency, and did not consider that beyond in our analysis. But at high frequency, we had already done some filtering in some previous analysis, so we think that we trust here what's happening in the wave buoys. Now, interestingly, in the middle, it seems like there is some overlap, so that's good to see. All right. So here I'm just showing some results, so selected result for just 3 wave buoys. And 4 models, so 4 parameterizations, so IC2, IC3, IC4M2, and IC5M2, which were not chosen for a very specific reason, apart that they span a range of different types of parameterizations. And we also include a no ice run. Now, obviously, if the no ice run consistently have higher significant wave heights, because of course there is no attenuations from the waves, and that's reassuring to see that when you include the ice, both in the model and the data, we have less energy. So indeed, the ice attenuates the waves. So that's reassuring. Now, if you look more carefully here at those patterns, it seems like the models and the data are not too far off from each other. Especially if you look at buoy 1 here, we have some nice correspondence, also in buoy 10, a little bit less in buoy 6. So the buoys here, by the way, are these green crosses, and all the models are behind. And then if you look at these different, why buoy 1 and buoy 10 are doing better than buoy 6, then all you have to do is basically look at the concentration below here. So at the start, especially here for buoy 1, concentration was pretty low. And for buoy 10, concentration was also relatively low, especially in the later stages, while for buoy 6, concentration was pretty high, remains high pretty much through the duration of the life of buoy 6. So it seems already that the performance of the models significantly depends on ice concentration. Now, if you look at the mean wave period, which is what you see in the second row here, then again we have similar results, so fairly good correspondence in low concentration, while at high concentration, that's buoy 6 here, all the model seems to significantly underestimate the mean wave periods by at least a couple of seconds. All right. So now let's combine all the buoys together and just look at these scatter plots here. So on the vertical axis, that's the model. On the horizontal axis, that's the buoys. And here, the top rows of these panels here are significant wave height, and the bottom row is the mean wave period. And in color here, you can see the influence of the ice concentration. And so again, here something consistent seems to emerge. At high concentration, we seem to have a bias that the model overestimates significant wave heights consistently, while the model seems to be performing slightly better, although maybe there's a little bit underestimates significant wave height at lower concentration. And for the mean wave period, again, these results are consistent across the different model parameterizations here, where especially at high concentration, the model seems to underestimate mean wave periods. So it seems like there are consistent bias here, which emerge at high ice concentration. So now if we look at the correlation coefficients, comparing all the models here together, that's the results that we get. Okay, so on the vertical axis, you have all the different models, including the no ice run, that the bottom one here. And on the horizontal axis, that's just the correlation coefficients for significant wave height and mean wave periods here on the right. And what I've also included here is a measure of bias. That's the color. Because it's interesting to see that the no ice run is highly correlated in a significant wave height to the observations. But if you look at the bias is actually the highest, and that kind of makes sense. Of course, if you remove the ice, then basically what you get is the forcing. So what this correlation means that the response and the forcings are correlated to each other, which is not surprising. So even though the no ice here has high correlation, it doesn't mean that it's a good model because it has large bias. But otherwise, clearly, we see that some models performing better than others, and some are doing very poorly, at least 4 of them here. And we have a few of them which are pretty good, both in correlation and in having lower biases. There's a bit more bias here in mean wave periods. And what we found here, and it's more or less arbitrary, but if you look at these models which have correlation coefficients higher than 0.5 in both significant wave height and mean wave periods, then there are 9 of them, and I've listed them here. So IC2, IC3, IC4, M2, and then a few more there. So these are the ones which we thought might have a better chance of working. Then we wanted to see, well, why does this happen? And so the attenuation coefficients, which is parameterized, in each of these parameterizations, then how does that compare to those actually we can compute from the data themselves? And so that's kind of my attempt here. So that's kind of a weird plot coming, but hopefully just keep with me for a second here. So that's my attempt of representing the range of attenuation coefficients as a function of frequency of all these different models. Now, these models, of course, depend on parameters such as ice thickness. So what I wanted to do here is represent a range of values of these attenuation coefficients for different ice thickness. So that's why you have this shaded region in some cases here. And then overlaid here, you have these data points here, and these are values of the attenuation coefficients as a function of frequencies, which were extracted directly from the data, to the Piper's data, and that comes from a paper we published a couple of years ago. And what's interesting to see here is that most of the models, most of the parameterizations for alpha seems to have alpha values lower than those that we measured. So when we see that the model seems to overestimate wave energy or significant wave height, then it could simply be a fact that, well, the parameterization simply of alpha are just too low, and the parameters which describe these models need to be adjusted to increase these values. All right, just one more result here, and that's potentially a bias, a reason to explain the bias that we observed here, especially in mean wave period, is, well, maybe the dispersion relation in the ice is different to the one in open water, and therefore the wave speed that is predicted by WAVEWATCH, which for most of this parameterization is the same as in open water, is not right, and that could introduce some kind of time delay here, essentially between the model and the observations. And so the question here, what I wanted to do is have a look at is correlation somehow improved if we time shift WAVEWATCH III generated data? And if you do that for low ice concentration, which I argue is a proxy for close to the ice edge, then you can see that here the peak on the correlation coefficients in significant wave height is as a timesheet of 0. So it seems like here there is no reason to think that the dispersion is wrong here. But if you look at higher concentrations, so larger than 85%, then here you can see that these curves here are clearly are not as clearly peaked here at t equals 0, and can be argued in some cases t equals 1, so that's the 1 hour, that is, that there could be a peak there. So it's possible that further into the ice here, basically the WAVEWATCH 3 is making the wave travel too slow, right, compared to what we observed. Okay, so just here to conclude, so it seems like WAVEWATCH 3 performs best for larger wave events and at low ice concentration. That is consistent. And also we observe clear biases in both significant wave height and mean wave period, which depend strongly on ice concentration. So most of these SIS parameterizations, which we used with their default parameter values, they underestimate wave damping rate or the attenuation coefficients. And also we found evidence that WAVEWATCH 3 slightly underestimate the wave speed, especially at high concentration or far from the ice edge. And so the next step, of course, here would be to look at, well, can we improve these model fits here by optimizing the parameters of these different parameterizations? One more thing that we haven't tested, but something that would be nice to look at is scaling this ice damping curve in WAVEWATCH linearly with ice concentration appropriate. And there's evidence that shows that it might not be actually based on observations. And then potentially might need to develop new parameterizations to improve the ones that are currently there, which I would argue none of them is likely to do the job consistently for all types of ice conditions and wave conditions. And that's me. Thanks.
Thanks a lot, Fabien. It's almost 10 o'clock now, but we've got a break for 30 minutes. So I think we can take a few questions for Fabien, and then I'm going to make myself a coffee, but we can continue some discussion in the break. But do we have some questions for Fabien?
Fabien, can I ask a question?
Sure.
Where did the linear relationship in concentration come from initially? Because I've always been very uncomfortable with it. It's certainly not obvious to me that if you increase concentration, you get a larger value of S. You should get a larger value of S, I should say.
I completely agree with you. I'm also very uncomfortable with that. The reason we did that is because everybody else before us did that. So we wanted to be consistent with,
I think Haley Shen introduced the idea, and it was probably based on the concept, probably scattering, the idea that you get more flows and therefore you got more scattering.
Yeah.
But if you think of turbulence and all the other things, it's not obvious at all to me.
No, it's not. I completely agree. I don't know the history of how this was introduced, but it seems to be consistently used in all these WAVEWATCH studies that I looked at ice damping.
I'll be interested to hear other people's views on that.
But also it's more than that. These other source terms, such as wind forcing, nonlinear wave interactions, these are also scaled by 1 minus concentration.
Yeah, exactly.
And that also makes me very uncomfortable, especially for the wind for the wind forcing. I mean, I think Alberto, I don't know if he's still around here, but I know he has some views that there is wind wave generation even at very high ice concentration potentially. So yeah.
I think they just a comment that those two ideas were definitely in that paper by Masson and LeBlanc in 1989. But how far back they go beyond that? So it's been
But that
around.
was, yeah, so that's a similar model to WaveWatch, but it wasn't WaveWatch. That's, yeah.
No, that's right. I think
Yeah.
WaveWatch hadn't been invented then.
Exactly,
So
exactly. Yeah.
they understood the idea of how WaveWatch was going to be, sort of thing. I guess that was what LeBlanc was working on. Yeah.
So do they have a linear concentration term in there? I forgot about
Yeah,
that.
and they had that idea of the 1 minus the concentration being the wave generation as well. Yeah.
Right.
Yeah,
Okay.
I think you're right, Mike. I think it was Masson and LeBlanc.
Okay.
It may go back further, of course, but like everything usually does, but it's been around forever and untested.
Randolph Falcon Scott.
Yeah, that's right. He had the idea. That's right. It was written down in the book and they dragged it out of his tent. Alberto.
Yeah, no, Fabien, I think Eric Rogers, in his data set of attenuation coefficient, he actually implemented two different parameterization, one weighted with the CI's concentration, and like not on the CI's term, but on the other terms. Some were weighted as 1 minus the CI's concentration, and some in a different version, it didn't weight them.
Okay.
So
I mean,
just to add to the the complexity and the confusion on how to weight all the source terms.
Right. Okay. Yeah. I mean, I remember reading a paper by Eric. I forgot which one now, which has a critical discussion of these scaling terms. I don't know how this is. I mean, how this can be modified in implementation of WaveWatch. Yeah, I'm not sure about that.
I'll look it up and send it to you the reference. Probably tomorrow morning because I'm getting sleep.
Yeah, no worries. Yeah.
Yeah, no, the delay. So you have a bias on the wave period. So the model has a slower or a higher or a lower wave period, remind me.
Lower, definitely lower by a couple of seconds, actually.
So a lower wave period.
Yeah, so you can see here on the the blue is a negative bias, which means it's lower relative to observations.
So it means that speed it's slower. So you
yes, that's right. Yeah.
So that might explain the other bit.
And that might explain that, of course, as well. Yeah. That. Yep.
Okay. I think it's time for me to call now.
I think we should stop the official discussion of the talk and we can have a break. We've got a break for 30 minutes. We can continue to talk and then we'll start the talks there. But let's thank Fabien.
Thank you.
Yeah, because now we're in the break conversation, Fabien. Like okay, so all the models muddle out in a sense, right? There's some are worse, but it's easy to be worse. Okay,
I mean, some of them are just wrong.
It's hard to, yeah, correct. But the actual ones that it's sort of clear to me that none of them are performing really well, and that clearly in some senses they're all wrong.
Yep.
So we need
now the thing is, so I didn't, I think, emphasize that maybe enough in the talk here. So we used each of these parameterizations with the default values of the parameters. Of course, a reasonable question to ask is, where do these default values come from, right? And for some of them, it's actually not clear at all. And for some of them, they come from optimization with respect to one data sets. So referring back to that, I think like Liu paper from 2020, which introduces IC5 parameterizations. These are sort of viscoelastic plate parameterizations. So they have these, so IC5M1, that's the Fox and Squire model, with some added viscosity. And I think the value they use for the elastic modulus was like 10 to the 14 or something like that, something ridiculously high. Now they use that value because that's the value that seemed to optimize the fit in that study they did to the data, which I think was a SIPEX2. But they used also the Robertson and Palmer model in that same study, which is, you could argue, a similar model, just viscosity is treated slightly differently. And for that one, the optimized value of the elastic modulus is 1 Pascal, 10 to the 0. So you have 14 order of magnitude difference between the two models.
But I think the point is that the models that essentially they've taken data and they've tuned it, but essentially you feed that measurement into the model. You're really feeding all the ones that fed in actual measured data in did better than the ones that didn't. So essentially, really,
but for that single data set.
Yeah, correct. But I think that what that says is that none of the models really what was happening is that it's the measurements themselves that are, they perform sort of well because they're roughly right. But obviously, the fact that the amount of wave attenuation measured in the Arctic in 1987 is not the same as measured in this. But
Mike, I think it's worse than that because both Fox and Squire and Robertson and Palmer are actually single plates of ice. And the experiments that were done at the time were on fast ice. Nothing to do with the marginal ice zone, but they're just a parametric convenience, I guess.
Yes, and I wonder if you went and said, here's a model for propagation of waves in a quark gluon plasma. I'm going to use that. I'm going to fit that model with the measurements that were made in it, and then put that into. It would probably perform just as well. It doesn't really matter where the model came from. It's just how well you fitted it to the data.
I mean, I think it needs to have it needs to have a few features such as frequency dependence of the attenuations. I think that's important. Other things, it's not clear.
I think that a lot of work to do on the modeling, that's for sure.
Yes,
that's what it's. I mean, because we were hoping that you'd get one of them would perform clearly better, which isn't the case at all. Like there's only some that do clearly worse.
a few of them are doing okay. I think that's the main outcome.
Quite a few, in fact, right?
Quite a few. Yes,
It's also great that you've done this, Fabien, because it's like you can hide things in plain sight. Like by having 25 different models, you've actually got no model, right?
Exactly.
Effectively, it's absolutely useless for anyone who wants to use it. But the only purpose for having all those models is for someone to be able to validate them, like you've done. But really,
and it's actually surprising that no one had done that before, actually. But
that's because. I mean, it's very complicated. It's great that they actually did it because it's very complicated to put these models into, like how you change the dispersion relation in WaveWatch would be so complicated. And
so some do it, but again, it's based on this viscoelastic, plate model dispersion relations, right? But some don't. So there's it's not consistent. But even those that do, that's the thing, even those that do, still you can see the evidence that you have this time shift issues. So it seems waves are still traveling too slow in the model.
And if you've got a 10-second or 15-second wave, it's there's so much water moving, it's hardly going to feel the ice. Its dispersion's hardly altered. Whereas if you've got a short wave, it's going to be much more affected by. So that's a whole...
but even that's the thing, because if you look at, I mean, what I showed here is even if you look far from the ice edge at high ice concentration, that's proxy for it. So you would assume that all the short waves have already been attenuated and are not contributing at all anymore. You still see that correlation could be improved by shifting the model by up to an hour.
Interesting.
So still waves are potentially traveling too slow.
Yeah.